So, good afternoon, ladies and gentlemen. Welcome to this week's colloquium. It's my pleasure to introduce today our colleague, Rainer Fries. So let me introduce him briefly. He did his PhD back in Germany, in Regensburg, in 2001. Then he moved on to Duke University on a prestigious Lünen Fellowship from the Humboldt Foundation for his first postdoc for 2 years, before then going to University of Minnesota for another 2 years of postdoc. At that point, he was kind of promoted there to a research assistant professor, but they could only hold him for 1 year because in 2006, we are lucky to get him here to Texas A&M on one of the Brigham BNL Cooperative University Fellowships, which made us very happy. And then 5 years later, he got promoted to associate professor with tenure. Rainer has done a wide variety of research, and he will report on that, so I'm not going to comment on that. Let me just mention some of his awards he received. In 2007, he received the Young Scientist Award from the IUPAP. In 2008, he received a Montag teaching scholarship from the university. In 2009, he got an NSF Career Award, and later that year, reaching into 2010, he was in Japan for a while on a fellowship from the Japan Society for the Promotion of Science, I believe. So we are very happy to listen to him here today to give us an overview and flavor of his research.
Okay. Thank you, Ralph. Can you hear me in the back? Okay, good. All right. So, yeah, I'm glad to be here. I thought there were some extra things that I need to do today as a colloquium speaker. I remember some of those very well from Saturday morning physics and other things. Okay, so I'm going to talk about nuclear matter in extreme conditions today. And so basically, there are some people among us that enjoy taking particle accelerators with the highest energies like LHC, and instead of putting in protons, they put in the really big stuff, big nuclei like lead nuclei and gold in the case of RIC, which is another such machine. And the question is why? They seem to derive a lot of pleasure from that. Personally, I'm not doing that. I'm not an experimentalist, but also looking at the results is indeed, as I hopefully can convince you, quite interesting. So, well, here's a, oops, the outline already went to number 2, okay. So here's the outline of my talk. I'll give you a brief introduction to why we do this, what we actually want to accomplish, some of the very basic parameters that are involved. And then I want to focus on 2 things that, among many that are interesting, that we've worked on here, myself, my group, collaborators here locally, collaborators at other universities. One is basically the very first instance of the collision and what's happening there, and that often is sort of summarized under the notion of color glass. And then the second topic that I'm going to report on is jets, which if you're in high energy physics, you're probably very familiar with. And is a topic that in high energy nuclear physics also gets more and more traction. And some of the most recent work is in this area. So, okay, now we have to go forward and ask the question. So why high energy nuclear collisions? Okay. So obviously what you can do with that, you can create very large energy densities, okay, energy per volume. And if you look around, where are systems in nature that we can emulate with that? So one thing that comes to mind, of course, is the early universe. Here's one of these famous pictures that I guess was made to celebrate results, measurements of the cosmic microwave background. But before that, somewhere here, there's a lot of other interesting physics as well. And what I'm going to talk about sits at times of a few microseconds, actually. So basically, the temperatures or energy densities back then, a few microseconds after the Big Bang, are comparable to what we can reach now at colliders when we put heavy nuclei in there. Another system where that maybe is not as obvious, but where something similar must happen are high-energy cosmic rays impinging on an atmosphere, or say a planet without an atmosphere. Then you have larger nuclei to scatter off, not just nitrogen and oxygen. So there is, of course, a lot of those cosmic rays are protons, but there is actually a nuclear component to that as well. So as heavy as iron-56 you can find, and of course the energies can also be very high. So it's just an artist's rendition of what this could look like. And so what you can infer then, if you think about what sort of the degrees of freedom are at those energy densities, and we get to numbers in a little bit. So you find out, well, this is the regime where the strong force among the four forces in our standard model, or well, 3 plus gravity, so one of the 3 in the standard model, where that force really is important, and where you actually get, where actually the phase transition between our hadronic world, where those strong degrees of freedom, quarks and gluons, are bound in protons and other bound states, neutrons, pions maybe, if you can excite them. So transition between this hadronic world and a world where quarks and gluons can roam free. So you can break confinement, which is a very fundamental property of QCD, the theory of strong interactions, by increasing the temperature. So what is plotted here typically is the temperature here on this axis, and the baryon chemical potential, basically to measure, to have a degree of how much sort of matter you have versus, in terms of baryons versus antimatter. And the reason is that at the beginning of the collision, you start out with a few hundred nucleons, which are, so baryons, which are matter, not antimatter. But then the energies are so much above 2mc squared that you can, of course, create lots more particles. So you can create proton, antiproton pairs, neutron, anti-neutron pairs. As we're going to see in the center of these collisions, you're basically net baryon free. So if you look at here trajectories that are taken in that phase diagram in collision. So LHC is not even here. The top Rick energy would be this. So we're almost baryon free where we actually measure. Okay, so, and maybe I should point out that the temperature for this phase transition is roughly between 150 and 160 MeV to our knowledge today. Okay, so here are the machines that my experimental colleagues are using. Since the early 2000s, we have the relativistic heavy ion collider. And the energies that are quoted here for PP and for gold-gold collisions, so the ones for the gold-gold collisions are actually per nucleon pair. So you actually have to multiply with the number of nucleons in that system to get the total energy. And at LHC, we're not quite at the top energies yet, but we have in the, if you collide lead, so it's basically a step up by a factor of 100 almost. We have about 5 TeV here in the collision. Okay, so here are some basic parameters that you can take home if you've never thought about colliding large nuclei. Okay, so to get the total energy, you have to multiply the beam energy basically by the number of nucleons that you have available. Okay, so so that's of order 100 usually, and so the total energy that you get then for RIC, for the relativistic heavy ion collider would be 40 TeV, and at the LHC you're actually pushing about 1,000 TeV. And if you convert that into units that you are maybe more familiar with, then these are basically macroscopic energies. So they're on the level of millijoules, micro to millijoules. Now, so here's sort of a cartoon here, and we'll see later how much of that comes close to what we can actually see. So here's sort of the nuclei ingoing. Now, they are not round, and the reason for that is if you're in the lab frame, you have a Lorentz contraction, which is actually pretty large at LHC. It's about 100 at RIC. It's about 2,500 at LHC. So because of the Lorentz contraction at the transient, sort of when the two are really overlapping, this is actually a pretty small volume, and you put all of that energy in there. However, it's not that all of that energy really does interesting stuff. It's actually just a fraction, as we're going to see. So the nuclei basically go through each other in some way. I'm going to explain very soon what I mean with that. But in between, that is where we're really interested. This is something new that is sort of created in that collision, and that's where we would find core gluon plasma, and then later on a hot hadron gas. A few of the dimensions that sometimes I'm throwing around. So the dimension of length here is Fermi is 10 to the minus 50 meters. That's sort of the appropriate length scale in nuclear physics and particle physics. And everybody's familiar with electron volt, I suppose. One more thing that we can maybe look at, because that's something I'm going to discuss also a little bit later on, is angular momentum. So if you think about a system where the nuclei are not colliding head-on but offset with an impact parameter, you can sort of look at what are the typical values of angular momentum that you get, right? I mean, obviously you have angular momentum, so you think R cross P with those energies. The energies are basically equal to the momenta. It's ultra-relativistic. You find about 10 to the 6 h bar, okay, at some typical impact parameters, which in terms of h bar is actually a lot, but it's actually not a macroscopic quantity, right? So h bar is so tiny that unlike the energy here, this is actually pretty small. What kills you is really that the impact parameters at which you expect anything interesting, of course, are measured in Fermi, and that brings it down a lot. Nevertheless, as I'm going to show, there are some interesting results now. People have not worried about this for a long time, but now we're sort of at a level of precision that we can actually do something about and understand something about angular momentum in these collisions. Okay, a little bit more about the basics of what happens when those systems collide. So this plot actually has some data points that are, I don't see, Chris is back there. He might recognize some of these. So what is measured here is the net proton number. So if you remember what I said before, that you start out with protons and neutrons, but you also create lots of particles simply because you have enough energy that you can make E equals mc squared work and sort of convert this kinetic energy into mass. But if you look at the net proton number, so you measure the protons minus the antiprotons, you find a picture like this. So these are different machines. Actually, I've not talked about these. These are lower energies. So the center of mass energy of the collision increases from here to here. At the time when the plot was made, LHC was just a fantasy. I mean, not a fantasy, but it was still being built, so there are no data points here. But you see that what I explained before, that the nuclei are basically going through each other. You can sort of read this off this plot, because the net proton number is basically, that's what you started with, okay? And I should add that this variable here, rapidity, okay, so it's rapidity, of course. I'm sorry. It's basically a stand-in for the longitudinal velocity or longitudinal momentum, and longitudinal meaning here along the beam axis. So you basically have the nuclei, or at least the quantum numbers, the conserved baryon number that is associated with that basically goes through each other. On the other hand, if you look at the total number of particles that is produced, so this is basically number of particles, these are just the charged ones, but never mind, as a function of basically the same variable, rapidity here, it's pseudo-rapidity, but again, for our purposes, we can assume they're just the same. You see that those peak in between. So if you would overlay those, you would have a very interesting picture. So there's sort of the stuff that went through each other, sitting out here at very large momenta. I should also add that the original momentum of a single proton, it would be here. So these nuclei really decelerate. So for Rick, it would be roughly about here. So there's really a deceleration, and that deceleration, that is what is used to actually fuel the creation of stuff in here, okay, and fuel the creation of these particles here. So only a fraction. I mean, we had fantastic numbers for energy densities before, but only a fraction of this energy really thermalizes. And if you look at this, the peak temperatures that you can reach are a few hundred MeV, and I'm I'm going to have a slide, next slide actually, where I can back this up a little bit also experimentally. But one more important point here. So you see at lower energies, the system, it's not really stopping, but it's sort of, the two nuclei sort of clumped together. They're still moving out. But here you have this very clear separation, and you get these plateau-like structures here. So, and that's because the remnants of these nuclei, they decelerate, but they stay ultra-relativistic throughout the collision. And that actually helps us if you want to do some theory, because it gives us an approximate symmetry. It's a boost symmetry very similar to Hubble flow that you can observe out in the universe. So these peaks here are not just, so this is not just momentum rapidity. So it's not just that these things are moving out very fast. They, of course, are also sort of the leading edge in space-time of what is traveling out after the collision, right? So you get an ordering where if you sit in the center of the collision, everything is sort of at rest. You would look at this stuff, or equivalently at this stuff here. And the stuff that is moving out very fast down the beamline after the collision is also very far away in space already, okay? So that is this boost symmetry, which helps us with some of the calculations. Okay, so now in a little bit more detail, what is sort of the, people actually sometimes call it the standard model of these collisions, but I think that's probably too strong. There might be others that still disagree with this, but it's sort of something where I think there would be a consensus of a lot of my colleagues that this is roughly what happens. So you start out with those nuclei, and basically your initial conditions, sort of at t equals minus infinity, are really the wave functions of those two nuclei, okay? And then you have this initial interaction here where they overlap, and so this is dominated by strong gluon fields. I'm talking a little bit about that in detail, and so this is what you can describe in this language of color glass. And sometimes people use for sort of what you create in between the two nuclei, then immediately after the collision. So at very early times, if you have a clock that sort of starts running at overlap, so sometimes people call it glasma. It's not something that a term that I like very much, but so the mixture of this glass and the plasma phase that comes later on. So then all this energy density that you've dumped in here, in terms of gluon fields, starts to thermalize, so it approaches kinetic and chemical equilibrium. Never really enough because the system is, or never really completely because the system is very anisotropic because of that Bjorkian flow. But you reach something that you can describe with fluid dynamics, with relativistic fluid dynamics, very early after the collision, about half a Fermi, maybe even earlier, sometimes in terms of time. And then you have this QGP phase, so you're way above the phase transition temperature. You have a QGP phase. Of course, you have tons of pressure that comes with that energy density. So you have an expansion also now in the transverse direction. Originally, all the motion was in the longitudinal direction. And the fireball cools and eventually reach TC. And then this interesting process has to happen of hadronization. So these quarks and gluons have to form protons and neutrons and pions again. And then you end up in this hadronic gas phase. And eventually there is a freeze out where all these hadrons decouple and then just free stream into your detectors. That's sort of the last phase here. Oh, hadron resonance gas. Okay, so yeah, so that's a particular way of describing the hadrons where the interactions are actually carried sort of by the resonances that can be formed. Yeah, rapidity. You want me to talk about rapidity? Yeah, okay, right. Okay, so rapidity, where do we have it? Okay, yeah, so rapidity was here. So rapidity is this variable that you get in special relativity that sort of stands in for velocity because it's additive, right? So it's a particular combination of energy and longitudinal momentum. And so basically, it's a proxy for longitudinal momentum. So, so for example, 200. If you have an energy of 100 GeV, for a proton here, it roughly sits at rapidity 6. Okay, so it goes like the log. You want me to write down the definition? Okay, all right. So it's a proxy for longitudinal momentum, really. Okay. MeV, so GeV, right? You mean GeV, yes. About 10 to the minus 22 seconds, 21 seconds. Yeah, so everything is over in a flash, which is, of course, one of the challenges. Okay, so, and glass, yes. I'm actually, I have a slide later on about this. So it means that certain things live on very long, on much longer time scales than other ones. And so I'm going to talk about that a little bit. Okay, so, okay, I have to see that I'm, yeah, let me talk about this, even though I probably have to speed up a little bit. So this is something that came out very recently and has not directly to do with nuclear physics. So I thought maybe I flash it. It's a result by the Atlas collaboration at the LHC. So it's not just that you get interesting nuclear effects. Of course, in the electromagnetic sector, at these high energies, there's also very interesting things going on. So what they observed is light by light scattering. So you have two photons that scatter into two photons that then have some transverse momentum, so they can be detected. So this is done in ultra-peripheral collisions. So you have sort of these nuclei just grazing and staying intact. And so then you get a very clean environment. And so, of course, the interesting thing here is that that you can have coherence effects that actually increase the yield of these photons. And if you look at this, it happens roughly at around 40 GeV at LHC. And this is where also, you know, in this region of a few 10 GeV, it's also where you can find the mass peak here for this two photon system. So this is an example of something that is not directly nuclear physics, but can be done in these high energy nuclear collisions. So, and of course, the effect here is a pure quantum effect via a fermion loop. Here's another electromagnetic measurement. So, yes. How do you detect? Well, you can detect photons. So the photons that you see in your detector have to have some momentum transfers to the initial longitudinal momentum. Okay. And then, right, and then there are background processes that are simulated here, and then you get a signal sort of above those background processes. Yeah, so, and photons, if you want to ask me what are the best detectors to detect photons in colliders, then I'll defer to my experimental colleagues. Okay. All right, so here's something I already alluded to a little bit, a measurement of the temperature. And it's very nice, but it also highlights some of the challenges that one has in this field. So this is a measurement by Alice, also one of the LHC experiments. So you measure the photons again. Okay, so now just single photons, and you plot the spectrum as a function of this momentum transfers to the beam. That is where you measure. And you notice there are basically two parts to the spectrum. One where basically on this log plot this is a straight line. So it shouts, well, exponential spectrum, okay? And then there's a curve that has actually a power law. So these are photons that are directly produced from the initial wave functions at overlap. I can come back to that in a little bit when I have a cartoon about this. But then you have these photons that live at 1 GeV, 2 GeV, and so on, which look thermalized. And if you do a calculation, what you would expect from a quark-gluon plasma and then a hadron gas, a hot hadron gas that radiates. Obviously, there are charges. It radiates photons. It is consistent with this. And then you look at just what you can directly extract from the data, and you find actually in the incoming graduate orientation, I tried to make this a little problem for the students. Didn't really get the answer, but anyway, so you can go through this, and let's just read off what the temperature is that Alice got here, and it's about 300 MeV. Okay. Now there's a couple of caveats, and that highlights the difficulty. So Hans had asked how long all of this lasts. So it's over in a flash. Okay. And we can actually, of course, we cannot insert measurements or make measurements during the collision. We can only look afterwards, right? So there is an entire history during that time, during that the system evolves, and during all of those, during that entire time, you can emit photons, all kind of photons, in particular those thermal photons, and you have to integrate over this. So this is averaged over time, from high temperatures to low temperatures. It's averaged over space, okay? So the anti-spatial profile of the collision. And in addition, you cannot really see this here, but it's blue shifted. We know there has to be an acceleration of that matter. It's really literally exploding. So there is actually a blue shift. So that is why one has to be careful with the interpretation of this. But if you do more detailed calculations and compare, it's actually looking pretty good. Okay, so all right. So this was sort of the general introduction a little bit to all of this. Here's a couple of important questions now that you can ask, with this at hand. So how is quark gluon plasma actually formed in these nuclear collisions? Okay, and are there new mechanisms of scattering in the high energy or high density limit? And I'm going to talk about that a little bit. How can we characterize properties of QGP and hadron gas? And what probes can be used as tools to further study this? So I'm going to talk a little bit about that. But there's a ton of other questions here that I will not be able to address. So what are the exact properties of the phase diagram? For example, is there a critical point in the phase diagram? New phenomena at lower energies. That's one trend at Rick also to go back to lower energies, look at systems where you have more of that net barrier number in there. Is there collectivity and maybe quark gluon plasma in smaller systems, like a proton, like a proton-led collision, which is a much smaller system, or even a PP, just a PP collision? And how far can we push the theory tools that we've used in nuclear collisions, where we sort of think everything is on firm grounds? How far can we push this to really small systems? All right, so let me tackle the first topic that I want to talk about in a little bit more detail. And so this is this color glass. Okay, so why color glass? So color, of course, refers to, well, quantum chromodynamics. The charges are colors instead of electric charges. We have color charges. And the glass is because there are different time scales involved. The time scales at which the actual nuclei are evolving are much longer than the time scale of the collision. So that is why we can sort of look at the wave function of the incoming nucleus as being frozen during the collision. So talking about this nuclear wave function, so if we increase our energy in the collision, we sort of reveal more and more features in the nuclear wave function. And here's a cartoon of how this would work. And this is best understood or quantified a little bit in terms of this variable x. If you've done some particle physics, you know it as Bjorkian x. It comes from a very simple kinematics like this. If you produce a particle with a certain momentum transfers to the beam, what is the energy fraction that you need in the incoming partons? Which energy fraction of this projectile here does it need to carry in order to create this? And the answer is, well, x is about 2 pt over ECM. So ECM over 2 is, of course, just the energy of one of those two things in the lab frame. And pt is basically the energy of what you've created here. So in terms of this Bjorkian x, then you can characterize certain regimes. Okay. So, for example, if you're in particle physics, you usually look at things that are fast or heavy. So like the Higgs boson, which has a very large mass, and then the calculation would be a little bit different, but you need a sort of a moderate to large x for that. If you create jets, I'm going to talk about it a little bit, you look at hundreds of GeV objects, maybe a TeV object, you need large x. So in particle physics, you're usually looking at x, at values of x that are sort of not too small. And then the picture that we have of the wave function of a nucleon is very simple. This here is, of course, really the simplest one with just the valence quarks, basically. But as you go to smaller x, you sort of fill up phase space with more particles. You have phase space available. But as long as you stay at large x, basically you are in a dilute scattering regime where you have just a process like this. You take one parton meaning a quark or a gluon, out of this, say, nucleus or nucleon even, and one here, and then you have sort of a 2 by 2 scattering, and that's it. And as you increase sort of the number of particles in your wave function, you might say, well, maybe I have to add a second one and a third one and so on. But of course, in the extreme limit, if you go to very small x, this can become very, very complicated. And it turns out now, if you look at the bulk of nuclear collisions, if you think back to the photon spectrum, where was the thermal spectrum sitting at, like 1 GeV, 2 GeV? Okay, so those are very small momenta that you need to actually create the bulk of that of the material that you create there. So you're sensitive to small x, and this is a dense scattering regime. And then the question is, how can you deal with this? So you can sort of do some kind of perturbation theory, starting with this and stacking them up, or you can go to the limit where you use the classical approximation, where you basically you have all the tree graphs together. So there's no loops, but you have all the tree graphs, and you can do a classical theory of the scattering of gluon fields. And so in this, you can ask, when does this happen? Well, this happens when these gluons sort of start to overlap. It's also called the saturation regime sometimes. So instead of just radiation, as you go to smaller and smaller x, you also have sort of a fusion, and that is characterized by a scale. QCD is really a theory without a scale in the classical form. But here in these bound states, you actually get a scale, and it's called the saturation scale. That's sort of just to throw out a number at Ricker LHC, you have to think maybe 1 or 2 GeV are appropriate. It's an energy scale. Okay, so the picture that you get, sort of this effective, so you can do an effective theory based on this picture, where the sources are basically your large X partons, okay, which are frozen during the interaction time, as I've said, and the small X partons you actually calculate, and they're sort of described by these classical fields. They evolve in time, and everything is sort of connected by the Yang-Mills equations and the covariant current conservation. So the Yang-Mills equations are the equations of motion for gluon fields. So you have these derivatives, which are now covariant derivatives in this SU3 theory, the field strength tensor, and they couple it to a current. And the current is basically, given by these initial wave functions. All right, so put a little bit more meat on it. So we often like to draw this in a Minkowski diagram. So here is the spatial axis along the beam. Usually we call that the z-axis. Here's time. So the world line of nucleus coming in, so here would be one nucleus, here would be another nucleus. They're basically over the speed of light. So they are these at these 45 degree angles. And they stay ultra-relativistic, okay? And they're frozen in time. So you just leave them there. It's an approximation. But at large energies, that should work very well. And let me talk about that later, but let me first say that, so these Yang-Mills equations are actually solvable for if you have a single high-energy nucleus, so you can sort of solve here and here. And a long time ago, also, it was immediately recognized then in this picture that you can write down the boundary conditions, what happens sort of here at the boundary, leading out from this point of overlap. Of course, there are two more spatial dimensions that are missing here. And then people started solving this. So the equation of the forward light cone, that is after the overlap. So then really the two fields interact. And in QCD, unlike in QED, where photons don't interact directly, they only can interact via these quantum loops. In QCD, gluons see other gluons. Gluons have color charges, so it becomes a nonlinear theory. It's complicated. So there's numerical solutions available. And but you can also do some analytic work here. And we've actually found, quite a while ago, we found a recursive solution for the fields here in the forward light cone after the overlap. So the fields that basically connect then and make up that stuff after the collision between the two nuclei. And I'm going to talk a little bit about this work here with a former student of mine, Guang Yao, where he actually calculated event averages. So for certain observables, not directly observable, but things that can at least then use for further evaluation based on these recursive solutions. This approximation to color glass, so this purely classical approximation, is also called the MV model after these two gentlemen, McLaren and Gopalan. And let's just let me just say one more thing about these sources here. Or the currents here that you have to plug in. So in these currents, or these currents are generated by color charges, right? So the color charges, those are quarks that have color charges. They can be gluons, and you summarize that with a density in projectile 1 and projectile 2. And then if you want to do event averages, you actually have to integrate your observable that you've calculated as a function of those two with a weight function, and McLaren and Gopalan sort of tells us what that weight function is. I'm coming back to that in a little while. Okay, I think these are really my only formulas or heavier formulas here. So just to show you sort of the system of equations that you have to solve. So those are written down. The problem was formulated about 20 years ago. So these are the equations that you get from the Yang-Mills equations in a certain gauge. When the gauge is fixed a certain way. And these are the boundary conditions that you get on this light cone here, that you get here. So you have the boundary conditions here, then you have to solve inside. And as I said, so this happened about 20 years ago. Since about 15 years, we have some numerical solutions started with SU2, and now people can do it in SU3. But if you check, so if you plug in those these equations here, you will find that up to this order in time that they also solve these equations. So once you have that, once you have the fields, there are just three here. The fourth one is basically fixed by the symmetry. You can calculate the energy momentum tensor. That is something that you're really interested in for the further time evolution of this later on. You can calculate the energy momentum tensor of the system after the collision as a function of these nuclear charge distributions. Okay, before I go on and discuss some of the results, let me point out something and why there is sort of a trend to event generators, what we call event generators, which are also very popular in high energy physics. So the detailed initial conditions for a single collision are basically completely unknown. Okay, so my experimental colleague can tell me what sort of nucleus they've used, right, and what's the beam energy, and everything else is basically not known. So what is the impact parameter? What is the spatial orientation of the nuclei when they collide? What is the configuration of the nucleons at impact? And then, of course, if you would zoom in more, so is there any information about how the quarks and gluons are distributed initially? We don't know. Okay, so some of these things, there are actually experimental techniques to get something out a posteriori, some information out a posteriori about some of these, but it cannot really be sort of steered. So what can you do? So you can model the statistical distributions for these, unknown initial conditions. Okay, so so you have to try to find out what are reasonable assumptions. Some are pretty obvious. For example, distribution of impact parameter, no problem. But others are maybe less so. So, but once you have these statistical distributions, very much like what I've shown here. So these are statistical distributions for those color charges in the two nuclei. Then you can do two things. You do that integral that I showed you, that I just flashed back to, and you get event averages. Okay, so those are expectation values, assuming those distributions, or you do a sampling, and that leads you to simulations event by event. Okay, and it turns out that this entire business is very much dominated. In many aspects of it are dominated by fluctuations, and so then you have to do this, basically go this way and do event by event simulations in order to catch all that physics. All right, so okay, let me talk a little bit about the physics that you get out from this from these analytic solutions that you can write down to these early time gluon fields. So here actually, just for to give you a flavor, two simulations that are done. So numerical. So these are numerical solutions to these Yang-Mills equations. One that's available for a couple of years, and this is a very recent one. So this is an energy density in the transverse plane, right? So you collide like this, and then you take sort of a slice through there and you ask, well, how is the energy distributed in the transverse plane? You can actually see how much it is dominated by fluctuations, right? It's very noisy. And this is sort of, here's the longitudinal coordinate also. You see this, these fields, these longitudinal fields that are created immediately after the collision in the simulation here. If you look at, so it's very noisy, and and it's numerically expensive. So we've advocated analytic solutions to go after some of the mechanisms that are actually behind of what you can see. And here's, I give you two examples. The first example, that wasn't us. That was actually known already for quite a while. It's basically part of these initial conditions. So if these two nuclei overlap, and just assume they're basically slabs of color charges now that interact, okay, for this particular purpose, what you get is, when they separate again, you get longitudinal electric and magnetic fields. These are chromoelectric and chromomagnetic fields. But you can write down QCD, classical QCD, with energy momentum tensor, just like in regular electrodynamics. And the interesting thing is this is already a non-abelian effect. So these fields come from commutators of the initial fields A1 and A2 in the two nuclei. Okay, so that's actually something that is known already for a while, but you can easily see that. The next thing is then, if you ask what is sort of next, what comes after this, what is the classical glue dynamics giving you after this? And it turns out you can sort of invoke Faraday's and Ampere's and Gauss' law, like in physics 2.8, to figure out what happens next, and that there is sort of transverse fields that are created from these longitudinal fields, from these changing longitudinal fields. There are some that are even in rapidity, or you could also say in this in the longitudinal coordinate z. There's really no difference for the argument here. Those are the ones that come from Ampere's and Faraday's law, and then there are some that are odd in this coordinate here, and those will be interesting when I talk about angular momentum in a little bit. They come from Gauss' law, interestingly, and I don't have time to go through this, but if you want to ask me later, I can maybe walk you through this. So this is sort of an abelian, like QED or electrodynamic like thinking, but at least formally, all you need to do is you need to replace regular derivatives by these covariant derivatives, and you get the correct result. Okay, so here's the energy momentum tensor that you get, and let me just point out two things here. The initial energy, so the diagonal of the energy momentum tensor, if you're not familiar with this, it's the energy density, which really is something just like 1/2 E squared plus B squared, also in QCD, okay? And here's the pressure in X direction, pressure in Y direction, and pressure in the longitudinal direction, okay? And you see the pressure in the longitudinal direction is negative. That's what you would expect. That's what you also get in a capacitor, actually, because the forces are actually, right, you have opposite charges. The forces are trying to pull this together, not to try to push to the outside. And yeah, and then there are more terms, because this actually goes to, I guess, third order in time, but we're not really interested in that for now. And this here is basically the pointing vectors. So this is sort of the pointing vector, E cross B, of the gluon field. So this is the flow of energy. So this is how the system, if you look at it as a system that has an energy density and a pressure, and now under that pressure starts to flow, this is how these are these terms. Now, and these are sort of mystery symbols here, epsilon 0 and alpha and beta. Let me just tell you that all these coefficients have been calculated and known explicitly, starting with the energy density, and basically we've calculated all up to fourth order in this paper here. So what you can do is you can then compare these results that you get at early times with numerical event average simulations, and that works out pretty well. And then you can go and maybe explore a little bit more. Okay, so now let me show you one application that I think was neat to use the analytic results for, because it's sort of tricky if you do just the numerical calculations. And that is a question of angular momentum. So luckily, we've already calculated sort of the total angular momentum that's available in a collision, say, at LHC. Now, it's sort of impressive, as I said, in terms of h bar, but maybe not really macroscopic. However, there's been a lot of excitement the last year or two or so about a new measurement from a star experiment where they found a non-negligible polarization of lambda particles. And there's an experimental reason why it's easier to measure this for lambdas. It's a UD, as up-down strange bound state. And it's aligned with the total angular momentum direction in the collision. This is as a function of beam energy. I said that at RIC there's sort of a tendency also to go back to lower energies. So you see this effect here. It's actually more pronounced at lower energies and sort of dies out a little bit at larger energies. There's another quantity called V1, but maybe I skipped that for now. So why would you get the polarization, of course? Well, if you have angular momentum in the collision. And the question is, at high energies, can you actually see that? And it turns out it's very easy to see if you take the analytic solutions here. And what you have to look at, well, how can you? So now we're looking into the plane that is here's the transverse coordinate where you have in which you have an impact parameter. Okay, so here's an offset. And here's a longitudinal coordinate. Basically, it's a rapidity, but just take it as a longitudinal spatial coordinate. And you look at terms that are basically odd in this coordinate, okay, because that would give you something like this, and that are even in this coordinate, okay. And then what you see is you find these terms here very easily, and they're all related to this beta. To these terms that I called beta here. And if you go back, they are the ones that come from Gauss' law here, from these rapidity odd transverse fields. So it's very easy to look at this, to plot this. This is not the entire pointing vector. This is just the part that contributes to angular momentum. But you see, so there's other stuff superimposed, and then you wouldn't see that structure anymore. That's why it's not plotted. But you see a vortex here that is sort of aligned, and you see some shear flow that is anti-aligned with the angular momentum. Okay, and you can go on and calculate. So the way to quantify it is, of course, to write down this generalization of R cross P. So instead of P, you have to use the energy momentum tensor. Then you get to this rank 3 tensor, which, however, in some of its components, again, has these well-known sort of the L's, Lx, Ly, Lz, or I call them L1, L2, L3 here. So when you integrate, because these are densities, so you get an angular momentum density, you have to integrate over volume. And then the one that is non-zero is, in the coordinate system that I've chosen, is sort of the y component, so L2. And you can write down expressions of how this component this angular momentum is built up at mid-rapidity as the collision progresses, and you get some pocket formulas from this that tell you how much you actually get. And at typical time scales where you expect this classical gluon phase to cease and sort of make way for something else, you get about 10 to the 2, so about 100 h bar at LHC. So that's much smaller than the initial angular momentum, and it's consistent with the fact that the signal within the error bars at LHC is actually 0, so we expect it to be small. So just a word to what you would do next, or what you can do next, and what we have done next. So these classical gluon fields, or this classical gluon dynamics, should only take you to very early times, about maybe 0.2 Fermi over C. The anti-collision might be 15 Fermi over C, all the way to freeze out. So the to-go theory over the last 15 years, because it has been proven to be so good in describing all kind of data, is the viscous relativistic fluid dynamics. So in a sense, so you sort of see in the data, or at least the data seems to imply, that the system is thermalizing very fast, and so you can run viscous fluid dynamics codes that describe the cooling and the expansion then in this phase that basically goes from 0.2, 0.5 Fermi over C all the way almost to freeze out. You could run it all the way to freeze out if you wanted to, and get pretty good results. So the way you match these two phases, the classical gluon phase and the fluid dynamic phase, is by this sort of this instantaneous thermalization assumption right now. It has important physics missing. It is certainly not completely instantaneous. It's very fast, but it's not completely instantaneous. But in event generators, this is still sort of the state of the art. So this is what we've also done here to sort of follow through with the calculation of angular momentum. And then we've used viscous hydrocode viral that we've developed here. And so what you see is, because you have viscosity, viscosity is sort of the natural enemy of shear flow. That is, if you look up the definition of viscosity, shear viscosity, that's what shear viscosity does, right? It tries to stop layers flowing like this. And so this, together with the boost symmetry at the beginning, is really so the explanation for the smallness of these angular momentum in the end when you can measure it. So the next steps in this is there's if you really want to match to the more interesting region where you actually have measured this polarization, you have to break boost invariance, and there's a couple of ways you can do that. There's also the gluon spin contribution that you can look at. That's something that is a rather fresh idea. And we've also looked at this event by event, and maybe I don't go through the details here. Maybe the impression that you can take away is that it is dominated by fluctuations. These are actually events that are averaged of about, there are already about 100 events that are averaged here. And this is an energy density. You still see a lot of fluctuations here. If you're interested, we can talk about it later. Okay, let me just stop by here quickly and say, and tell you that, so how did we create pictures like this? So I told you that these analytic solutions, what you do is you integrate over these statistical distributions in the initial state. You get event averages, but you can also sample and get event by event calculations then. And so we can use these recursion relations actually also to build a fast event generator. So instead of solving Young-Mills numerically, which is numerically expensive and takes half an hour or more for an event, you can run in maybe a few minutes and get nice results. And yeah, I don't really, I have some preliminary results here, but I don't really have time to talk about this. Okay, let me take the last 5 minutes or so. Okay, to talk about something else, and it has a relationship with what I talked about before, in a sense that it also involves, in part, event generators, or the push to event generators. So to run large-scale simulations. And the example that I have here is the one of jets. So if you remember this picture of sort of this dilute scattering. So if you have particles that scatter at high energies because they carry a large initial momentum fraction. So what does a quark or a gluon do that is created here and has maybe 100 GeV or 1 TeV? So it will not thermalize. Okay, it will make a jet if you're in high energy, what is called a jet. If you're in high energy physics, you're very familiar with these things. It's basically a bunch of hadrons that all travel together in a collimated way, and you can see them in the detector like this. Now, this is a collision actually not in pp. If this were proton-proton, the energy in this jet and the energy in this jet would be the same. This is from the CMS experiment. Well, Taruki or anybody's here. But anyway, but this is in nucleus. And if you look at the numbers here, this jet has about 200 GeV. This one has about 70 GeV. Why is this odd? It's odd because these things, if you give a kick to this particle, right, 200 GeV in this direction, because of momentum conservation, the other one better also have 200 GeV. So this jet has lost about 130 GeV trying to punch through this quark gluon plasma. So that's an entire separate field, not separate, but a different aspect of heavy ion collisions that is becoming more and more important now that LHC experiments are running. So here's a plot that shows the suppression. So even at 900 GeV, this is a quantity that basically asks how many of those jets do you lose at a given momentum. The expectation is one, that you get sort of 100% back from what you get in, and the suppression is almost 1/2. So let me skip. Maybe I say a few words about this. So there are two collaborations that me and some other colleagues at Texas A&M were a part of to look at this. One is the jet collaboration, and so capital J, capital E, capital T. Our main contribution was to develop the physics and also the software for hadronization of jets in the nuclear medium. And let me just point out, so this is a non-perturbative process that in QCD has to be modeled. So there's no real guideline from first principles, unfortunately. But there's very successful models that exist for 30 years, like string fragmentation, cluster hadronization, that are used in high energy physics, but they don't scale or they don't generalize very easily to jets in a medium. So our contribution was this recombination model. So this is work done with Jim Minkowski here and Kyung-Chul Han. And I'm not going through the details of the model. In the end, it turns out to be a hybrid model between a coalescence process of quarks and string fragmentation for particles that are still moving very fast away from everything else and sort of don't have an overlap in the wave function with other quarks. So the model compares, so the challenge is really with the existing models like string fragmentation, as it is, for example, in this event generator Pythia, to sort of reproduce this for the physics for jets in the vacuum. And these are some plots that sort of show you that indeed that was accomplished. These are distributions of hadrons inside jets, different hadrons, pions, kaons. This is the longitudinal momentum distribution inside the jet. This is the transverse momentum distributions. So this gold standard we've sort of hit. And so if you ask what is the effect if you put a jet in the medium, what is the effect of this? How does hadronization change? There are basically two effects that you expect and that you can observe. One is you alter the jet chemistry. So it's easier to make baryons, for example, than in vacuum jets. That's been something that has been observed very early on at RIC and has been very well described by these coalescence processes. And the other one is sort of an additional broadening step that you get that is not there in string fragmentation. And that is something that is being explored. And then the last thing is, so JET was a physics collaboration that really looked at the physics. So currently, this has been sort of replaced by JETScape. So this is a new collaboration, NSF funded, that is active since last year, which is not just theorists in the field, but also experimentalists, computer scientists, statisticians. And the key here is to sort of make a framework sort of for the next generation of event generators. And the problem, maybe I gave you a little bit of a flavor now that we're closing, but maybe I gave you a little bit of a flavor that there's a lot of little niches and areas where you have a good description of one or the other aspect. You have dilute scattering, and you have very dense scattering, and you have thermalization in one part and not thermalization in another part. So you have good descriptions often in certain parts of this sort of theory space, let's say. And so this should be a framework that allows you to put these aspects together. So for example, to have a fluid dynamics, to have a sampling of initial state, to have an initial state generator like the color glass that I talked about, fluid dynamics, hadronization, and then here are these Chet-Shaw Monte Carlos, which I don't really have time to talk about, but they all work sort of on different aspects of the physics of these jets in the medium. And I think somebody tells me I'm out of time. And that's okay. So I think this is my last slide that I'm going to show. So the first beta release of the software. So this is really the money for this collaboration comes from computation. the computational part of NSF. So we'll have a first beta release of the software later this year. There will be a winter school that goes with this. It looks like this right now if you run it, but it's not really public yet. And so the local work that I work with Michael Cordell on, and also with Stephen Rose. So Rose is doing the fast color glass event generator, and we're continuing the jet work on hadronization, and all of this will go in and will actually be used for analysis. Okay, so I'm out of time, so let me just throw up some conclusions here. So high energy nuclear physics has some, I think, unique opportunities and challenges. I should have written opportunities here too. So there's some very interesting things that are going on and unique things going on. There's a lot of things that we still need to accomplish experimentally and theoretically. What I've talked to you about in detail is progress in understanding of the initial gluon phase, the event generators that are sort of the next step and need to be reliable and fast. I talked a little bit about understanding mechanisms with analytic solutions to this. Emphasis on angular momentum, but there's other things that you can understand as well. The jets, I didn't have time. I had a slide for heavy quarks. This was some work I did with Ralph Rupp here, actually. So they can be probes of quark gluon plasma and hot hadron gas. There's a lot of interesting things. So probes of basically the interaction of these probes with the medium are a separate test of the medium. And then I talked a little bit about these collaborations, and in particular Jetscape, that will give us a flexible framework for these event generators in the next decade. The future, well, there's a lot going on experimentally. So STAR is going to low energies. There will be a new experiment at RIC actually called S-Phoenix, replacing the old Phoenix experiment that will start in the early 2020s, that focuses on jets and some heavy quark physics as well. LHC, and there's at low energies also new facilities that will come online in the next over the next 10 years or so. Okay, that's it. Thank you. Oh, well, yeah. No, there is more in the collision. Yeah, let me go back. Yeah. Hold on. So, what I calculated there was dl d eta. So this is per rapidity slice. Okay. So because I use the boost symmetry. Now it's too far. Okay, because use the boost symmetry. So this is only the angular momentum that lives. Here we go. Right? Yeah. This is only the angular momentum that lives sort of between -1/2 and +1/2 in space-time rapidity. Yeah. Yeah, but you cannot. The problem is you cannot just multiply, because this is not a boost. L itself is not a boost invariant quantity. So so one has to be careful. I mean, there's actually a dependence on eta here, right? So that's why you see. No, where do I have it? Oh, here. So you see, so it's not a boost invariant quantity. So you have to. I think if one wants to compare to another model, what one should do is one should take that other model. Yeah, and look. Right, and cut that in space-time rapidity and look what one gets there. I think that would be the better comparison. Yeah.
In this early initial gluon as you get these color flux tubes, etc., presumably one parameter that could be able to grow out of that from this construct at whatever level of
Yeah.
you go would be the equivalent of the backfield color screening.
Yeah, there's right, and it's Okay, so I think what you're talking about is actually, now let me go to this plot that I skipped over. So there is a characteristic length scale here, and this is so this is an so this is the transverse plane again, and what is plotted is actually the longitudinal flow, but you just give it one color when it's sort of in one direction, and you make it a different color when it goes in the other direction. And what you see are typical domain sizes, sort of. So these are actually domains, and these domain sizes go with the saturation scale. So that is the length scale. So these flux tubes actually have the size 1 over QS, typical size 1 over QS. The theoretically easier way or a cleaner way is not to look at stare at this and look at this, but you can do a correlation function between gluon fields at different points. You plot that correlation function. It has a certain width, and that basically gives you that natural length scale that is created there. Experimentally, this is hard to access, but of course if you look at the gluon, the saturation scale also in principle is in the early gluon spectrum. So if people do calculations, you can do a calculation also. So this is all done in space-time, but you can also use sort of a factorized approach in momentum space, like people would do in high-energy physics, PDF, Parton distribution functions with a cross-section and calculate this. So this QS would also appear in sort of in the Parton distribution function of these gluons, and you can in principle sort of the typical momentum that you get, intrinsic transfer momentum that you have, and you can in principle access that in experiment as well, but it's sort of a different. It comes from somewhere else, right? It's not directly an apples and apples comparison, but theoretically we know it sort of has to be the same. I mean, these are related quantities. This, something like that, directly to access with experiment, I think that's not going to happen. Yeah. So that's a nice picture to have, and yeah. So does that answer the question? So you can access the saturation scale experimentally, roughly. In for example, if you look at things like proton nucleus or deuteron nucleus collisions have been done at RIC, and so there are certain features that you get that where you're very sensitive to the saturation scale in the nucleus. Mm-hmm. Ah, yeah. Okay. Good. Very good. In my list of the future, I actually omitted that. I realized. Yes. So the Electron Ion Collider is sort of the next big project in the U.S. that the community wants in the U.S. It's not quite clear yet if it's going to be built at Brookhaven or at Jefferson Lab. If it's going to be built at Brookhaven, the physics case that they make is very much has a lot of this color glass physics in it. So indeed, you can then probe deep into this color glass regime. So it depends a lot on the machine parameters that are being discussed. So Jefferson Lab people want more luminosity to look at very rare processes, completely unrelated to this. And yeah. Yes. Right. So you will have a much cleaner environment to probe, for example, these distribution functions, gluon distribution functions in a nucleus. I mean, that's one of the things that you can do, and that would also give you access to the saturation scale then.